I don't know, particle filters or particles. Let's explain.
No, Jesus, I managed to turn on the transcript. How do I take this off? It's gonna be terrible.
So are there people online actually? Yeah, there's. Yeah. Okay.
Okay, so well, I'm going to talk about. There are some links with optimal transport, and hopefully enough. I'm going to talk about some work that some things that I've encountered while working on a paper with Jennings and Adam. It's the paper's up on arXiv. And it's the final version. It will be published once AI stats happens in a couple of weeks, but we're not going to change the draft anymore. So if you like any more information about anything that I say today, that's the place to go look. I give references as well, which I'm going to skip a lot today. And yeah, if you like any references at any point, just stop me and ask. Or if you have any questions, stop me and ask. And if you're lost, please stop me and ask. The only thing worse than being lost in a technical talk is being lost in a 3-hour-long technical talk. So. Okay. Oops. Sorry. Let's do this. And here. Okay, I'm going to start with a disclaimer. I'm going to skip all sorts of technical assumptions, details, and conditions that you need to make everything that I'm going to talk about rigorous and really imbue it with meaning. I'm going to do that just because they're some are a little bit involved, some are a little bit repetitive, and today I'm just going to aim to give some intuition about the relevant ideas and not these things that you need to fill in if you want to do it properly. Now, if you'd like to do that, the books of Ambrosio and Villani are filled to the rim of this stuff. And also you can ask me to follow up on any details that I skipped. And there's actually also people here that are better versed in these things than I am, or I suspect they are, like Nick, for example. So they're good people to ask. Even better that way, I avoid having to answer any real questions. So, and yeah, throughout I'm going to do things like assume when I write a derivative, I assume it exists, an integral, I assume that the right integrability, measurability conditions are satisfied. I'll write densities all the time when I mean the corresponding measure and assume that measures have densities and these sorts of things. Okay, so with that out of the way, I'm going to start with the sort of high-level ideas that motivated this work. And if you take nothing else home with you today, but you take these things, I'd be content. And they're pretty simple. It's just some problems in computational statistics and statistical ML are optimization problems, or you can rephrase them as optimization problems if you take a little bit of care. And sometimes, not always, but sometimes you can do well by treating them as such. And by that, I mean by trying to solve them using an optimization algorithm or something like one. In particular, once you make this connection, you gain access to kind of the arsenal of tools and methods and theory that have been developed for optimization, and that can be helpful. Now, these are not revolutionary new ideas. There's loads of people in the world thinking along these lines, especially in ML. But I do think that we exploit them a little bit less than we could in some circumstances. And today I'm going to try to persuade you of their usefulness by just going through an example, taking a couple of these problems, rephrasing them as optimization problems, and then trying to solve them with this approach. Now, you might be wondering what this has anything to do with optimal transport, and the connection is Otto calculus. That is a chunk of theory and ideas that were developed primarily in the optimal transport literature, but elsewhere as well. And it lets you do this, at least take some approaches to this, of trying to emulate an optimization algorithm. And I'll kind of expand on what I mean by this. So I'm going to start with one of these problems, and should be pretty familiar to this audience, is that of approximating an intractable target distribution. So we have some target P, some probability distribution that we're interested in, that we'd like to compute integrals against, but it's intractable in the sense that these integrals don't have closed form expressions. The underlying space X is high dimensional, so approximating this thing numerically is not trivial, and you kind of have to work on that. In particular, we're going to be interested in finding an approximation Q to P that is tractable. So another distribution that is somehow similar to P, but that we can easily compute integrals against it. And in order to do that, I'm not going to assume that we have access to P itself. I'm going to assume that we have access to an unnormalized version of P, rho, and I'm going to use set as the normalizing constant. You know, the usual kind of like Bayesian inference sort of setting. And by access to rho, I mean that we can evaluate its rho itself pointwise and its gradients. That's it. Now, I'm going to take this thing and rephrase it as an optimization algorithm. And I'm going to do that by doing something pretty dumb. And my dumb thing involves the KL divergence, which is this guy here that is, the off chance that anyone is familiar, something that takes in two distributions, P and P dash, and spits out a real number. And it's a divergence in the sense that it's non-negative. It's for all P and P dash is greater or equal than 0, and it's 0 if and only if P equals P dash. So you can use it as some sort of surrogate of distance between P and P dash. It's not a distance, but okay. So we want to find a Q that's close to P. Well, we can say minimize the KL divergence from Q to P over all Qs in the space of probability distributions on our underlying space. Now, this is kind of like a trivial problem because the solution is P itself, and that's the thing that's intractable. So this doesn't really meet our needs. But in reality, what I'm going to do is I'm going to stick with this kind of grandiose aim, and I'm going to come up short at some point. I'm not going to be able to do this over all probability distributions, but over some and some that are tractable. Okay, so I'm going to rephrase this problem again. And using the fact that the KL divergence, you can rewrite it as the free energy plus the log of the normalizing constant. And the free energy looks the same as the KL that I had before, just that I replaced P with its unnormalized density. And then the normalizing constant doesn't depend on Q. So minimizing this guy over Q is the same as minimizing that one. So I can rephrase my problem as minimize the free energy over all distributions Q. Which then leaves you the question, can we do this using an optimization algorithm? It's an optimization problem. And, well, I mean, the answer is yes. There's a huge literature built on this idea called variational inference. People do this all the time. And there, what they do is they take this big space of distributions and they restrict it to a nice tractable parametric subset or family in their jargon. So a bunch of distributions Q parameterized by some parameters they'll call the variational parameters. And they'll take these. This might be like mean field Gaussians, and the parameters phi are the means and the covariances. They'll take this parameterized form of these distributions, they'll plug it into the free energy, they'll get an objective in terms of the variational parameters, and then they'll minimize that using their favorite optimization algorithm. And often one of these like first order methods that improve on gradient descent, like ATOM or ATOGRAD or RMS problems. BFGS you see as well sometimes. Okay, say you didn't want to do this because this involves having to choose this family, and what's a good family to use is not such a straightforward question because you should choose a family that has distributions that are close to the target itself, and that starts raising problems because the target is hard to work with. And in reality, most people just pick this out of practical convenience, which families are easy to compute and optimize over. So you don't want to get involved in this whole thing. Let's go back to our original. Can we minimize the free energy not over a variational family, but over the space that we actually care about using an optimization algorithm? What about something like gradient descent? The first thing that you're going to encounter if you open an undergrad textbook on optimization. So I'm going to try to look for something like gradient descent that I can throw at the free energy. And let's start easy with gradient descent for minimizing functions on Euclidean spaces. Very simple algorithm. It says you start, so here I'm working on the plane. You start somewhere and you take a step in the direction of the negative gradient. So you move perpendicular to whatever contour line you started on. Then you update the gradient, you take another step in the direction of negative gradient. So moving perpendicular to whatever contour line you landed on at the beginning. And you keep doing this up until the gradient vanishes, so you stop updating, which means that you've hit something quite flat, so a stationary point. Okay, so in order to look for an analog of this guy that applies to the free energy on this more abstract space, I'm actually going to look for an analog of the continuous time counterpart of this algorithm. So what you get by taking the step size h down to 0, or in other words, updating the direction of the gradient more frequently. And what you get is just a smooth curve moving through space, continuously going perpendicular to whatever contour line it's on. And this curve, well, it satisfies this ODE over here called the gradient flow. And it just says exactly that. At each point in time, move by following the gradient, the negative gradient. Okay, and to get gradient descent back, all we have to do is do an Euler discretization of this guy, and the step size of the discretization is the step size in gradient descent. So I'm going to look for an analog of the gradient flow that applies to the free energy, and then discretize and approximate until I recover something that I can run on my computer. So the analog is going to look exactly the same. It says you update Q by moving in the direction of the negative gradient of the free energy. And at this stage, you might say, hold on, what do you mean by the gradient of the free energy? We all agree what gradients of functions on Euclidean spaces are, but this is kind of weirder space. So it turns out that what you really need to define a gradient on an abstract space is a metric on that space. And this is not exactly right, but just to give some sort of intuition, it's if you're somewhere and you want to look for the direction of greatest ascent, right, the normal idea we have of the gradient or its direction, you want to consider all the little steps you can take around where you are and pick the one that increases the value of the objective the most. Right? In order to be able to reason about this, you need to define what you mean by a little step, by a small step, and that's where the metric comes in. That make hopefully some sense. Okay, so I'm going to go more into detail later. I'm going to come back to this. But for the time being, I'm just going to choose the Wasserstein 2 metric, in which case there's this sort of turn the crank procedure. Once you have the metric to obtain expressions for the gradient, assuming a bunch of technical things work out in the meantime. And this is the kind of stuff that was developed in Otto calculus. So if you do this for the Wasserstein 2 metric, you'll end up with this expression of the gradient. And this thing here, you can just think of it as a sign density that tells you how to move in the space of distributions. Okay, so once we have this expression, we can just plug it into the gradient flow to get our gradient flow a little bit narrowed down. And you get this thing here, which you can think about it as an ODE on the space of distributions or as a PD over the underlying space. And I think a bunch of you will probably recognize this equation. I'll come back to that in a second. But right now, it's nice to just stop and run a couple of sanity checks. You defined a notion of a gradient. So straightforward to ask, what are the stationary points according to that notion? Which Q's make this gradient vanish? And it's pretty easy to check that the only Q that makes this gradient vanish is our target P, which is good because this is the point that we're actually interested in. And it's not really difficult to see. If you want to make this thing disappear, you basically need to make this gradient here disappear. And the only way to do that is for this log ratio to be a constant. And the only way that can happen is if Q is proportional to rho. Or in other words, but Q is a probability distribution, so it should be rho normalized, that's P. And some technical assumption somewhere. But and if you work a little bit harder, you can start proving convergence under very general conditions of the flow to the actual target, to the actual P, to the stationary point. And this is a very old result. There's a million versions of it. If you want to see a very kind of general Lassalle's invariance principle that you can extract this from, it was in this paper by Carrillo from this year. And they give references to all the history of this thing. They're better equipped to talk about that than I am.
Can you repeat the metric that you are using?
I'm using the Wasserstein 2 metric from optimal transfer. The same thing we've been talking about for. Yeah. So
another sanity check, is this guaranteed to preserve the fact it's a probability measure?
Mm-hmm. Yeah, that's a really good question. Yeah. So actually the way to see that is if you integrate this thing over X here, and you apply integration by parts, so the gradient goes to a constant, this whole thing vanishes, meaning that if the mass of this thing is 0, so if you move in this direction and you have mass 1, you're going to have mass 1 plus the mass of this, which is 0, which is still mass 1. So you keep a probability distribution. And I'll come back to this as well in a little bit. Okay, so we have very good reasons to believe that if we could just solve this flow for all time t and just run it for a while, it would take us very close to the target that we'd like. Of course, you can't. This is intractable for two reasons. First of all, we have a continuous time axis, and that's like a no-no, right? You need a recursion to run something on your computer. And on top of that, it's a PDE whose domain is the underlying space, which we've been assuming is quite high dimensional. That's not a trivial thing to solve in general. So I'm going to deal with these things by either using a bit of theory or approximating until I get something tractable. I'm going to start with the theory, and I'm going to start with the PDE. And here, well, as some people here probably recognize, this equation here is actually the Fokker-Planck equation for the Langevin diffusion, for these SDEs here. And what I mean by that is that if you can solve this SDE and you can find the law of xt and call that qt for every t, and you collect all of those, then those qt's satisfy the equation. Okay, so now if I can only approximate the law of this guy, then I will get an approximation of the solution of that guy there. And in order to do that, I'm going to use this other kind of little fact in which that the empirical distribution of this process here approaches its like law, space distribution as t goes to infinity. And by empirical distribution, I just mean what you get by following the path of the SDE, of the process, and averaging over this path. Okay, so we got rid of the PD, and all we're left with is the continuous time axis.
And is that convergence also in massive starting distance?
But this is where I start deferring questions to others. It depends on. I know for like chains in discrete spaces it is, and it'll be convergent in some version. We can look it up if you like. Okay, so continuous time axis, I deal with that doing the simplest thing I can think of, which is throwing Euler-Maruyama at the SDE to discretize. And you get these recursions here for a chain whose path approximates the path of the SDE. And to approximate the empirical distribution, well, I just do the usual piecewise constant approximation to an integral, and you get basically the empirical distribution of this chain. And this chain should also be quite familiar to people here. It's just EULA, the unadjusted Langevin algorithm. That's literally what I ended up getting in probably one of the more roundabout ways you can actually get the unadjusted Langevin algorithm. Now, before moving on, I should point out that this is not the only way you can do this. We can go back to here and skip the empirical distribution altogether. We can just focus on this guy here, on approximating the law at time t for every time. And, well, how can we do that? We can use Monte Carlo. If we're able to generate what I call a bunch of particles, these x1, x2, and so on, capital N of these, 10, 100, 1,000, whatever, and we can make sure that they all have the same distribution, and these particles have generated them in a way that they're independent, then the law of large numbers tells me that their empirical distribution approximates their joint law, QT. And to generate these particles, you can do just about the dumbest thing you can think of. You can take this equation here, copy paste it capital N times, and drive each of them with an independent Brownian motion. Right? And then you can discretize with Euler-Maruyama just as before, and you get something that is going to look a little bit trivial. You just get capital N unadjusted Langevin chains, all running in parallel. And this time, you basically average over the particles instead of over time, and that will give you an approximation of of the flow at the discretization point. And then you can run that for long enough, and that hopefully will approximate your target. And in reality, you're probably going to end up doing a mixture of these two things. So you're going to take that and average over time as well. And these things, this is kind of really trivial comment, but they have a distinct advantage of doing this, that you can vectorize computations across the particles. And that means that you'll get them to run a lot quicker, even if you have the same theoretical cost that's just running a single chain in parallel. And in practice, you're probably just going to spin out, I don't know how many of these things, and run them on a bigger machine, if you need, if your target is complicated enough to require. Okay, so I want to just take a step back and recap what I've been doing for the last 20 minutes. I've taken one of these problems in stats and ML, and I've rephrased it as an optimization problem, that of minimizing the free energy over the space of probability distributions. Then I chose a metric on the space, which let me obtain an expression, a corresponding gradient. And using that gradient, I plugged it into the gradient flow ODE, which gave me a gradient flow to aim for. I found a process whose law satisfies that gradient flow. And then I discretized and approximated that process until I got out some recursions I can run on my computer. Now, this is a pretty general recipe you can throw at other problems. You can try to, at least. It won't always work, but often you can actually get it to work. And I'll give you another example later, maybe a less routine one. And even in this problem, you can start tweaking this recipe to get a whole bunch of other methods to solve it. The same thing. So for example, you can switch the metric with respect to which you're defining gradients. So if you switch to the Stein metric, you'll get SVGD, or Stein variational gradient descent, that Liu and people published around 8 years ago or so. If you switch to the Wasserstein-Kalman metric, or what people are calling it, these days, you'll get ensemble Kalman filters that Andrew Stewart and friends were looking at. You can also change things a little bit more. You can try to not emulate gradient descent, but emulate another optimization algorithm. So if you aim for momentum or acceleration, you're going to get things like underdamped and kinetic Langevin algorithms coming out. If you aim for stochastic gradient descent, you're going to get SGLD. If you have a target that has, like a non-differentiable, like an L1 penalty or something in it, you can look for an analog of proximal gradient, and you'll get the thing that Pereira did a little while ago, the proximal Euler coming out. And this right now, so these are 3 different algorithms plus gradient descent, that's 4. I've gone over 3 different geometries. So you can do 12 permutations here to cover a bunch of things that are out there in the literature, hit some that are not out there. And I haven't even started messing around with the discretization scheme that you use. Now, this is the dark side of all of this stuff. You can basically keep cranking out a never-ending different approaches for these algorithms. And that might be good for writing papers, not always the most interesting. More interesting is which is a good one. Which one's actually worth it, and in what circumstance?
Can I ask you a question?
Absolutely.
So the particles that you notice, the examples are independent, or you can couple all of them?
No, so
They can come on.
in these, they're not independent, and that's the difference with Euler. And the update for one particle involves all the other particles, so these end up with an n squared cost, whereas the number of particles, and the other thing just ended up with n. But ours is a bit of a shame, because you worked all these particles, well, ours, what I've been talking about here, and you don't really use any information from one particle in the other ones, right, to update them in a smarter way, and this is what these guys tried to do. On the flip side, this blows up your cost, and it'd be nice to find out some middle ground, something that you don't have to use all n particles to update each different one in a different way. And end up with it.
Sorry, basic question.
No.
Because I think I'm missing something. What's the definition of rho again?
It's just the unnormalized target. No,
Unnormalized pi.
Yeah, sorry.
Yes. Okay. So you have the unnormalized target, and then you stick it in the Langevin diffusion,
Yeah.
and
then you get unadjusted Langevin for that target.
okay.
The normal.
Okay, but this sounds like standard M60, right?
This is incredibly standard. This is just a
okay.
long-winded way to get very standard stuff.
Okay, so what's the relation with rho and this procedure and variation inference and the optimization problems? I understand.
Like through this approach, you can kind of think of Euler as an approximation to gradient descent, and to the gradient flow applied to the free energy.
Oh, it's the same thing essentially. Oh, it's the same formulation. It's 2 different formulations for the same problem. Is that what you're saying?
It's similar.
Okay.
In variational inference, you take the free energy and you want to minimize that over all possible probability distribution. You say that's too hard, so I restrict this to a simple parametric family that I choose.
Yeah.
And then you run an optimization.
Yeah.
The approach I was trying to follow was instead saying, I'm not going to restrict to the variational family. I'm going to try to define something like an optimization algorithm over all the distributions. And then if you do that, you end up getting these SDs and things coming out if you're doing grading. And then I started approximating at that stage.
Okay.
Right? And then you end up with Euler, and you haven't had to pick a family.
Okay.
It also has, one thing that is nice about doing that is that when you pick a variational family and you go to the parameters, you start optimizing over the space of parameters, while really you want to be optimizing over the space of distribution. So you don't take into account any sort of geometry or distances or whatever that you want on the space. And actually people in BI do spend time doing all this natural gradient stuff, in which they're basically trying to take the notion of gradients that you would get if you were working with Fisher-Rao on the spatial distribution and pull it back onto the parameters. Sorry, that was a bit of a mouthful. We can, I like talking about these things, so we can. Yeah, actually, it's a good point for questions. I'm literally about to stop or hit a question point.
So regarding that point, so is there any reason why? So I understand that intuitively that it's probably better to not restrict your family and discretize later. But yeah, is there any result or intuition maybe that tells you that somehow the flexibility that you gain by not restricting your family but discretizing later is somehow larger than the flexibility you could get?
I mean, look, I'm not convinced that one approach is better or the other. And right now, realistically, the biggest things that are fit out there are fit with VI, not using particle stuff just yet. But it'd be interesting to see how far this goes, and that's kind of what we've been chasing. Some things is this thing that if you're still doing gradients in the space of mesh, that stuff, you're kind of working a little bit, respecting the distances that you really want to be working on instead of, and natural gradients, you can do it in some VI cases, but not in others, because you have to use the Fisher matrix and inverting, and in some cases that's tractable, in other cases that's really expensive, so you can't always. And other things here, always, if you blow up the number of particles, you can approximate as well as you want, generally, hand wave, but you have the option of it. If you pick mean field Gaussians, you're going to be stuck with mean field Gaussians regardless of what you do, right? So you're only going to approximate up to so much. Whether it's worth that extra approximation quality or not, that's a different answer. No worries. So yeah, I said I did these things. I mean, I did them an incredibly hand-washy sort of thing, right? And if you were tracking the amount of hand-waving, not hand-washing, wishy-washy hand-waving. So if you're tracking the amount of hand-waving that I was doing, you probably saw it peak around there. I said I derived this gradient. I didn't, I just stated a formula. And that's what you need, that's where autocalculus comes in. And that's what I'm gonna now get into until we get to a point that we can be working these gradient expressions at least formally, not without the technical stuff. I don't know, there's questions, or is it too early for a break? Possibly.
For a break now?
Yeah.
I don't know.
I can do it otherwise in like 20 minutes or so.
I think good 30 minutes.
Everyone's still keeping up okay? Don't need an injection of caffeine or something? Okay, any other questions? Okay, so autocalculus is a differential calculus for abstract spaces. And by that, I mean a collection of concepts like gradients, derivatives, Hessians, things that have to do with change, and rules for manipulating them, product rules, chain rules, and so on. And these things that we take really for granted in Euclidean spaces, but extended to these sorts of spaces of distributions and other things like that. It's named after Felix Otto, who was playing around with these things in the late 90s. And he was doing it in the context of these spaces of distributions and Wasserstein 2 metrics on it. I think he was actually messing around with the free energy as well as something to be taking gradients and doing stuff. So probably one of the more routine extensions of calculus from differential calculus from Euclidean spaces is the one to Riemannian manifolds. The sort of things you see in like a differential geometry course or an introductory one. And if I had to sum up autocalculus in a sentence, and it's probably doing a bit of a disservice, is treat these abstract spaces as if they were a Riemannian manifold and apply the same sort of definitions and rules that we use in that case. Now, they're not Riemannian manifolds. The spatial distributions is not for a bunch of technical reasons, so not absolutely everything holds, but most things hold. So if you just do that more often than not, you'll end up in a reasonable place, and then you can check the technicalities to make sure you haven't messed up something. So that's what I'm going to try to go over, and I'm going to go piecemeal. And in order to do this, I'm going to make my life as easy as I can, and I'm going to restrict the space of all possible distributions to be that of distributions that have a strictly positive density with respect to some reference measure, dx, and I'm going to, equate a distribution with its density. I mean, I've been doing this throughout, but I'm just being more explicit about this now. And the reference meshing I'm going to use, well, it depends on the underlying space. If the underlying space is Euclidean, I'm going to use Lebesgue. If it's discrete, I'm going to use the counting measure. And if it's something else, I'm not going to say anything. And I'm going to carry on doing these things of assuming integrability and measurability conditions and so on without mention. Okay, so in order to, again, autocalculus, treat the space like a Riemannian manifold. In order to do that, we need three things. We need tangent spaces, we need cotangent spaces, and a Riemannian metric. And I'm going to go through them one by one, in case anyone doesn't remember these things. So let's start thinking geometrically. This is what I think of when I think of in this space, in my head. The space of distributions, I think of a unit simplex, sometimes in an infinite dimensional space, sometimes in a finite dimensional. It depends whether the underlying space is a finite space or it's not. And for some underlying spaces, like this one here, in which I only have three elements, 1, 2, and 3, it is really the unit simplex, because it's the set of three-dimensional vectors with non-negative entries that sum up to 1. Here, I'm already starting to put this greater than 0 instead of non-negative because of this assumption I'm doing about strictly positive densities. So in our case, it's the unit simplex excluding the edges. And if you go to the general case, and because I'm doing this thing of equating densities and measures, it looks exactly the same. It's the set of functions mapping from the underlying space to R that are positive everywhere and that add up or integrate out to 1. And you know, this is really a special case if you think of vectors, three-dimensional vectors, as mappings from this to R. Okay, so tangent spaces. Tangent spaces. We have one of these per point on the manifold. So at each Q, we have a different tangent space. And the tangent space, it's a linear space that contains all the directions that you can move in without leaving the manifold. For our case of the space of probability distributions, all tangent spaces are copies of the same space. It's not like a circle or something that you need to change the line as you move in different places. And they're pretty easy to describe. If you go to the cartoon, it's just a set of three-dimensional vectors that add up to 0. Because I'm at Q and it adds up to 1, it's non-negative, and I take a small step in one of these things. I don't change the mass, still probability distribution. So, general case, same sort of thing. Functions mapping from X to R that integrate out to 0. Okay, and normally people put a subscript here to say the tangent space at Q, but because these are all copies of the same thing, I'm going to drop the subscripts. Next up are cotangent spaces. A cotangent space at a point, we have one of these per point on the manifold. The cotangent space at a point Q is a space dual to the tangent space. But there are slightly different definitions of duality, depending especially in these infinite dimensions. So I'm just going to choose a space that is dual, and by that contains something like linear maps on the original space. And I'm going to do it in not probably the best way of doing it, but using something I call a duality pairing to make life simple. So what is a duality pairing? We have one of these things per point on the manifold. It's just a mapping that takes in tangent vectors. It takes in cotangent vectors at that point, and it gives you back real numbers. It's a bilinear mapping. So you should be thinking of something like inner products and flat. I'll show you soon what it looks like in our case. And just as before, because the tangent spaces don't depend on the point that you are, they're all copies of the same thing. The cotangent spaces are all going to be copies of the same thing, and similarly with this duality pairing, so I'm not going to be writing these subscript Qs everywhere. So if we're back on this cartoon case, with a unit simplex in R3, then the cotangent space is the set of three-dimensional vectors modded by constants. Yeah.
One more question. Are they all copies of the same thing because the metric is constant or something?
We haven't touched the metric just yet. It's because...
Oh, because it's flat.
Yeah, I'm a bit wary of saying flat because then I get told on, because when you put metrics, then there is a notion, but yeah, it's because you can always move in the same directions.
Okay.
Actually, you know, if I had included the edges, that's not true. If you were on this edge, I would have to be talking about a tangent half plane. And if I was in a corner, I'd be having to talk about tangent cones. And this is one of the many reasons I'm not including the edges. Did that make sense? Okay, so tangent space, for our case of spaces of distributions, the cotangent space, sorry, is the set of vectors, of equivalent classes of vectors that differ by an additive constant. That's a bit of a mouthful. Let's try to make this more concrete. This is the duality pairing I'm going to use in the cartoon case. It's just the standard Euclidean inner product, right? And it takes in a tangent vector tau and a cotangent vector v, and that's it. Nothing fancy there. Now, our tangent vectors tau, they add up to 0, right? So if I replace v with v plus a constant here, then I end up with the same thing, right? Because I end up with c, the constant c, times the sum of the entries of tau, which is 0, right? Yeah.
Why are we making the assumption that that's some zero? Now, you know that's the definition, but why is that the definition?
Because if I was a cube and I moved in a tangent vector tau, I want to remain on the simplex, so I want the mass to remain 1. So if tau didn't add up to 1, then I would stop being a probability distribution. Make sense? Cool. So that's why you get the slightly weirder thing with the mod in the cotangent spaces here. And here I'm doing the usual abusive notation of conflating a vector with its equivalence. Now we want to go to the general case. Good news is it's pretty easy. I just replace three-dimensional vectors with functions on x to r. And I replace the Euclidean inner product with the flat L2 inner product. And I say replace, I'm really just generalizing the previous case. I've just gone from a counting measure to a general reference measure. Is this making sense? And here, the functions, we have to also mod them by constants for the same reason. Anyone confused?
What does this star signify here again? I missed it.
This means the cotangent space. Yeah. And this means the tangent space. And star is cotangent because it's meant to be dual, or have a kind of duality sort of interpretation.
So when you say functions that differ by an additive constant, you mean, let's say, a base case, a function, and then another one in this equivalent class would be that plus c.
Exactly. That's cool. Okay, so now all we have left to deal with is the metric, the Riemannian metric. And a Riemannian metric is a collection of inner products on the tangent spaces. So this collection is indexed by the points of the manifold. So we have one inner product per point on the manifold. And that inner product is an inner product on the tangent space at Q. And what do we do with these inner products? We do everything that talks geometry. So angles, lengths, all these things. That's where we use the inner product for. So I'll run you through some examples. You can first off use the inner product to measure the length, the size of a tangent vector. Are you going to move a big step or a small step? And you use it by doing the induced norm by that inner product. You can use it to measure angles between two tangent vectors by using the usual cosine formula. You can use it to measure lengths of curves. So if QT is a curve parameterized that going from 0 to 1, the parameterization, it's something like, well, I shouldn't draw because I draw terribly. Something like that. Then its derivative is going to be a tangent vector because it's the thing that points you where you're going. So we can do this norm on it to measure how big of a step it is. And then you just integrate that over the entire path. And once you have lengths, you can start talking about distances. Because you can say, okay, what's the distance between two distributions, P and P dash? Well, I look at all curves that join these two distributions, I measure the lengths, and I pick the curve with the shortest length. Or the geodesic as well. There you can start. And you can carry on producing more geometrical concepts with these things, but I'm going to stop because there's a finite amount of time in our lives. Okay, to work with metrics, I'm going to work with something that I call tensors. That's how I'm going to define most of these metrics. Tensor is not quite the right word. I use it in terms of like multilinear mapping. The right word is something like, it's the metric in local coordinates, but our local coordinates are the same everywhere, and tensor is a lot shorter to say than that entire phrase over and over and over. So what do I mean by a tensor? By a tensor, I mean a collection of linear maps, one per point on the manifold. The one at a point Q maps from the tangent space at Q into the cotangent space. It's linear, it's invertible, and it's positive definite. And what I mean by this is that if we do this thing of taking a vector tau, a tangent vector tau, pushing it through the tensor into a cotangent vector, and then I do the duality pairing with tau itself, this thing should be strictly greater than 0 for all non-zero tangent vectors. Yeah. Yeah, it's a space that is kind of dual to the tangent space, so it should define linear maps on the tangent. Okay. But in our more concrete case, it's just these sorts of things, like vectors modded by constants or functions modded by constants. Okay. And you can then, you use kind of these things to define linear maps on the taus. If I replace their tau with tau 1 plus tau 2, this is linear. Okay. That's kind of the linearity. It's a bit of a pain to actually set these things up and think about it. Is that okay? Okay. So let's try to make this a bit more concrete. These tensors really are not that mysterious. If we're on this cartoon case, where the tangent space is three-dimensional vectors that add up to 1, then these things, they map into the cotangent space, and those are three-dimensional vectors, also with a mod in it. So this is just a 3 by 3 matrix that is positive definite on the tangent space. So the quadratic form has to be greater than 0 for all tangent vectors are non-zero, and tangent vector means that the entries add up to 0. Like if they don't add up to 0, I don't care. This could be whatever, 0. And in general, you can have many of these things, and I'm going to give you one of them, and this is called the Wasserstein 2 tensor, and Wasserstein 2 Riemannian metric is the associated. Oh yeah, sorry, I don't know if I skipped this. Here, I use these things here to define an inner product, to define a metric, and you can check that if the tensor satisfies this thing, this is an inner product. That's why I use these things. So now I'm going to define one such tensor and the corresponding metric, and this one's called the Riemannian, the Wasserstein 2 tensor. And we define it in terms of the inverse, because we don't have an explicit formula for the tensor itself. And the inverse is defined by this. The inverse maps cotangent vectors to tangent vectors. And it does it through this formula here. And V is the cotangent vector. And you can check. This thing here, just to sanity check, this should be a tangent vector, right? So if you integrate this out over x and you do integration by parts, this will cancel out and it becomes 0, right? Which is what we need for a tangent vector. It has to have mass of 0. Okay. And then you could ask, what is the corresponding metric? And you can start doing some simple calculations. So, this tensor is invertible. So for every tensor, I can find a corresponding cotangent. So for every tangent vector, I can find a corresponding cotangent vector that maps through the inverse into that tangent vector. And I can do that for both tau and tau dash with v and v dash. So I can rewrite them using these things here. The inverses cancel, you're left with this. I have an expression for the inverse. I can plug that in and you get this thing here. You do integration by parts and you end up with this thing here. And that's actually that's the Wasserstein 2 metric, Riemannian metric, not distance metric. And you might ask why Wasserstein 2? And the reason is because the distance metric that is induced by this Riemannian metric is the Wasserstein 2 distance metric from optimal transport. And it's actually not hard to check. We have the expression for the metric. We can then define the length of any curve on this space. And, you know, basically here, that's where we're using the metric. So this VT here should map through the inverse of the tensor into the thing that is here. So VT should satisfy this equation here. And I want this to hold for every t. This is what people in optimal transport call the continuity equation. And then if you just go to the definition of the distance between 2 points, it's this thing, infimum over all curves that join those 2 points. And you get this thing here, which is the dynamic formulation of the Wasserstein to distance metric, or the Benamou-Brenier formula that Matt talked about before. I think Nick will talk about more later. And that's why the name. And I think this is, we can all do it with a break, maybe.
Sorry, what was in the underneath the infimum? What is this?
Yeah, V has to be such that it satisfies this equation here. Are there any questions? This was pretty heavy towards the end.
So the Riemannian matrix G is induced by Q, right? So GQ. So you start with a.
Yeah, I use this. I pick GQ and then I use this to get.
Okay, so Q was the distribution.
It's a point on our manifold, and our manifold is a space of distributions, so it's a distribution.
Okay.
And this is.
Start from Q, then there is a induced Riemannian matrix, right?
We have this space of distributions, and on this space we start building things. We put tangent spaces that tell us how we move.
Okay, so it's in.
And then
Index by
cotangent, and then, yeah, it's indexed by Q, sorry.
Okay.
So we use, basically you use a different inner product at different Qs,
Yeah.
because you might want to measure angles and distances differently at different places. You basically have a different compass and a different ruler at every point that you use on that point. That's kind of how people do like Riemannian.
Yeah.
And I'll try to give an example why you would ever want to do this later, of why, in Euclidean space, not in this. Any other questions? Things that were confusing?
No, I want the question. So the curvature, what does it represent? Morally?
Ask Nick. Yeah, sorry, I don't have a super short.
Okay.
I forget these things.
That's
And I shouldn't say. It's already bad enough when I'm talking about something I vaguely remember. It's even worse when I'm talking about something that I don't.
I might come back later on.
Yeah, I think.
Even we connect them to sound.
Okay. Should we have a coffee or a break?
We have maybe 20 minutes, 15, 20 minutes break, or?
Yeah, that works.
Okay. So we meet at 10:25.
10:25. Okay, I'll leave something here.
Sorry?
I'm really glad we had that last